Yes, Samajit, good evening. Okay, the question is, I have too many doubts from the assignment you sent us. Abradeep, okay. Okay, that assignment at least can wait for us some time over there. Okay, at least I just sent it yesterday in the night, so maybe give some time, at least a couple of more days, then we can. This time I will send the solution by the way, don't worry about that. It's already prepared. Okay, answer is, yeah, so this rocket question is saying, and basically a rocket chamber. The rocket is moving in a gravity-free space with a constant acceleration of 2 meters per second square along the positive x direction. You have to see the figure, which is drawing the rocket chamber as a rectangular box, which is accelerating along the positive x-axis with an acceleration which is equal to 2 meters per second square. And what is given by the distance as the length of the chamber inside is 4 meters. A ball is thrown from left end of the chamber in positive x direction with a speed of 0.3 meters per second relative to the rocket. At the same time, another ball is thrown in negative x direction. Okay. 0.2 meters. That is relative to the rocket actually. Time in seconds when the two balls hit each other. The acceleration of the rocket is 2 meters per second square. This first particle speed of 0.2 meters per second. But that is related to the rocket actually. And this one is 0.3 meters per second. Again, relative to the rocket. The length is 4 meters. In this case, we have to find the time after which, the time in seconds when the two balls hit each other. Okay. It is definitely useful to consider the entire situation relative to the rocket itself. The point in this case is that the rocket has, okay, repeat it. Orkodev, the question has been sent in the group. You should see that. If you're not able to see that, then let me repeat. The question says that there's a rocket which is moving in free space. This is the inside chamber of the rocket. Its length is 4 meters. The acceleration of the rocket is, okay, no need, fine, then okay. In any case, the acceleration is 2 meters per second square towards the right. Two particles have been projected from the rocket inside it. One is from left to the right with a speed of 0.3 meters per second with respect to the rocket. The other one is from right towards the left, 0.2 meters per second. We have to figure out the time after which they meet or they collide. Basically, they're moving or they're thrown on the same line. So the idea is if I consider, first of all, with respect to, well, actually, yes, with respect to some outside observer, if I consider that acceleration will be imparted to these two particles as well. The idea is that but it will be useful, for example, if I go over to the reference frame of the rocket itself, okay. If I look at with respect to the rocket, because all the speeds have been given with respect to rocket as well. If I move over to the reference frame of the rocket itself, it is not a projectile on it because the acceleration direction is same as the motion direction over there. So it is just a motion straight line over there. So in this case, with respect to the rocket, these two objects will have actually acceleration of 2 meters per second square towards the left. Okay, I'm just okay, I'll just give you how much time by the way. 3 minutes will be enough, or 4 minutes, not more than that. No. With respect to the chamber shown above, the acceleration is 2 meters per second square towards the left actually. Opposite. You can write down this something like this. We have seen earlier. The acceleration of the particles with respect to the rocket, the acceleration of the particle with respect to some inertial observer, let us say with respect to the Earth, for instance, or any other inertial observer, minus that of the rocket actually. This part is 0 because individually, with respect to the external observer, they are simply thrown some speed, so they don't have any acceleration with respect to the inertial observer. So this part is 0. So I end up getting that the acceleration of the particles, any particle, with respect to the rocket is nothing but negative that of the acceleration over there. That is what I'm saying. With respect to the with respect to chamber, the acceleration is not 0. Similarly, for respect to an observer as well. Well, I have to check the answer, Arunabu. Original poster has to give the answer. This part over here is 0, that part, and that is why acceleration of the particles with respect to the rocket seems to be minus. You can think in this way, by the way. The point is, any kind of uniform acceleration can be thought of as a gravity in the opposite direction, actually. In fact, it is impossible to tell apart a uniform acceleration with uniform gravity in the opposite direction. Okay, they are strictly speaking the same thing. No experiments can reveal the difference between uniform acceleration in one direction and a gravity of the same magnitude in the opposite direction, actually. If the observer is inside the rocket, then man will also have acceleration relative to 0. Yeah, the man will have the acceleration relative to, the acceleration of the man with respect to the rocket, that will be 0. But because the man is stationary with respect to the rocket itself. But then the particles are moving, isn't it? They are free to move. Let me see, Abradeep, how much chance you're getting.
Sir, acceleration how much should I take?
What?
Acceleration.
How much?
So acceleration. No, sir. Acceleration. How much should I take?
With respect to what?
No, sir. I'm
Rocket.
using the. Yes, sir. Means I am using the formula with AC equal to UT plus half AT square.
Yeah, so it depends which one you're talking about. If we consider this one, then
yes,
acceleration
exactly.
is this way. So in that case, you could write down UT plus half AT square. But for this particle, it will be UT minus half AT square.
Means then how much value should I take? Means the acceleration 10 or 9.8?
And at 2. Why should take 9.8? 2.
Oh, what's it?
There is no gravity in this case. You can think of it like that way, Swarnabush. There is nothing called pseudo acceleration. There is pseudo force, by the way. Acceleration is always real. There's nothing like pseudo. But yes, you might think of it this way essentially. With respect to inertial observer, there won't be any actually pseudo, but I'm just taking the reference with respect to rocket because the question already asked about the rocket. That is why I've taken the acceleration with respect to the rocket, and that is why it is coming to the opposite direction. For the first particle, if I consider this one, for example, acceleration this way, but about this one, it has an acceleration which is that way as well. So with respect to the rocket, the motion of this particle will be actually going this way and coming back over there. I could find exactly how long it takes to return back.
Sir, T equal to 8 seconds.
Getting 8 seconds.
Yes, sir.
I do not know the answer. Somebody has to tell.
Yes, sir.
Okay, let me see how much. First of all, if I consider the maximum distance with respect to rocket, I'm considering attained by the particle B. Let us consider this as B. That is A. So if I consider in this case with respect to the rocket, then obviously the rocket is not accelerating any longer because I'm already inside the rocket itself. Okay, Anushka, let us see. Uh, we find this case that if I look at the particle B, for instance, in that case, B will actually go this way and then return back because this motion is pretty much like the gravity, but the gravity is pointing in this direction and the magnitude is just 2 meters per second square actually. In this case, therefore, if I find the time after which it comes to rest momentarily with respect to the rocket, I can utilize the equation 0 equal to initial speed 0.3 minus 80, which is 2 into t. So time in this case turns out to be, this gives us a time as 0.15 second, which implies essentially that in 0.15 second it will come momentarily at rest. Meanwhile, at that particular point of time, I can obviously find a distance. The distance can be obtained either by using the formula v square equal to u square plus twice s. That I can do over here. This is the momentary rest of B. At what point it's happening, that is I'm looking at. B is coming to rest after 0.15 seconds being thrown, and it is going to be at a distance that is equal to I can find this one from here, 0 equal to 0.3 square minus 2 into the distance covered, S of B, or S, let's consider. So I get S in this case is 0.09 by 4 meter. It is negligibly small, by the way. It is 0.09 by 4 meters, so I can multiply with 100, I get 9 by 4 centimeters, which is roughly 2.1 y2t. The acceleration is 2 meter per second square, so that is why. The acceleration is 2 meter per second square. Okay. Yes, I think the answer is going to be 2. He wrote down somewhere earlier. And so I find it goes very, very small distance and then returns back. Fine. Meanwhile, at the moment when this comes to, obviously, if it's going to be 0.15 second to go that way, then obviously return back, and that will take 0.15 second as well. Total time of flight of this B will be therefore 0.3 seconds only. On the other hand, in that 0.3 second, how much distance this is going to cover, by the way? It's going to cover this way. The distance is equal to 0.2 into 0.3. I'm using ut plus half at square. So plus half into the acceleration into 0.3 square. That gives us 0.06 plus 0.9, which implies 0.15 meter, which implies by the time this particle goes this one returns back, this one has only covered 0.15 meter, by the way. Isn't it? It has only gone this way, only 0.15 meters. So quite obviously in this case it has way much larger distance to cover before it can meet the second particle. The particle B meanwhile has just gone this way and returned back. It's already on the on this rocket wall, by the floor in this case. So this particle have to come all the way till here to meet this particle B, which implies essentially I can just find the time by using ut plus half at square equal to 4 meters. No. Actually, there was a question in the WhatsApp group that you could check over there. No doubts that we have. Okay, it's given the WhatsApp. You can check. The last question will be this particular one. So I find this case the time can be therefore obtained by using the standard distance 4 meter has to be equal to 0.2t plus half at square. A is 2 in this case. So therefore I can utilize that idea to find out the time taken as 4 equal to initial speed 0.2t plus half into a into t square. That gives us a quadratic t square plus 0.2t equal to 4. In this case, the time square, I can write on this one as 2 multiplied by t multiplied by 0.1. So I added the square of 0.1 on both the sides. So I get 0.41 square. That is therefore t plus 0.1 whole square. turning out to be 4.01, which gives us the time t as root over of 4.01, but obviously I can neglect the minus sign, minus 0.1 second actually. That gives us in this case roughly how much? 4.01 is approximately 2 point something. Why are you writing so fast? I'm writing so fast. Is it? I'm just speaking up and writing the statement as well. Anyway, this is time I'm going to get. I can just use a binomial approximation. We have 2 coming up. 1 plus 1 by 400 into half. Quite small actually. It will roughly to be 2 seconds itself. Yeah. So we'll have to round it off then, it seems. It is root over of. Yes. Minus 0.1 actually. Yeah, so that is what we have. So that is approximately 1.9 second is what I'm looking for. 1.9 something something. State the question, Vibrata. It is can you check the WhatsApp? In that case, you could see the question. Okay. The last question, check it out. What have we done? Let the meeting point. Huh.
I have joined today, so the question is not with me, sir.
I mean, say, are you still in the? I mean, have I just? I mean, say, joined you to the WhatsApp group?
Yes, sir. Sir, today morning you added me.
I think you should get because this was forwarded just after. I mean, after some while ago. Okay, no problem. Today morning, isn't so you can see the WhatsApp group for the 11 physics part. Okay, anyway, I will just forward you if you wish.
Okay, sir. Thank you, sir.
Okay. Hold a moment. Yeah. So I forwarded you. Okay, Alberta.
Okay, sir.
And
Thank you.
again. Okay. Yes, Abradeep, what I did was I first checked in this case. If I consider this particle over here, it turns out that this will have basically with respect, everything is done with respect to rocket, by the way. Okay? All of these things have been done with respect to the rocket. With respect to rocket, the particles have an acceleration a, which is 2 meters per second square towards the left, in fact. This particle, therefore, has a kind of, it's almost like a free fall motion, gravity pointing that way. You throw something up, it just goes up and come back, something like that over there. I find that the time taken by this particle to reach its maximum height with respect to this floor is turning out to be only 0.15 second. I had the formula of 0.3 minus 80. That must be equal to 0. That gives us 0.3 minus 2t equal to 0. So that t equal to 0.15 second. So we find that 0.15 second goes upwards and then go back downwards once again 0.15 second. So total 0.3 seconds. It has just gone up and come back, returned to its floor over there. Okay. Meanwhile, in that 0.3 second, this particle is covered this much distance. I have utilized for this one the acceleration this way. So I consider 0.2 into 0.3 ut plus half a t square. A is 2 meters per second square. So I get in this case 0.15 meter only. This is 4 meter by the way. So it goes only 0.15 meters. And this one has already come back. Obviously, therefore, they can meet only when this particle reaches over there. So I have to just figure out how long it's going to take for this particle to reach that for cover at 4 meters. That's why equated 4 must be equal to ut plus half a t square once again. And that gives us the time as this much, which is approximately turning out to be 1.9 seconds over there. That is what I should get in this case. I'm not getting, it's 1.90 something, so I can't still approximate to work of gravity. Yes, Ankit, I said, actually was saying just now that any kind of
Sir,
uniform, yes.
sir, is the rocket moving vertically upwards or going horizontally?
What do you
Sir,
think?
it is.
In
Sir,
a gravity free space, do you know what is the vertical, what is the horizontal?
sir,
How do we tell which is vertical direction on Earth, for example? It's nothing but gravity direction, isn't it? Imagine, for example, rocket ship is in this case. A rocket ship is, for example, moving in free space, and it has an acceleration which is equal to 9.8 meter per second square that way. Now, for an astronaut over here, which will be the vertical direction, by the way? What do you think? We tell about vertical apart from the other directions by the sense of gravity. Wherever the gravity is pulling us, that is vertical for us. Okay. And in this case, actually, effectively from inside the rocket, it seems as if there is a gravity this way. And that gravity is only not 9.8 meter per second square, but only 2 meter per second square. That is what it feels from inside this rocket actually. That is what I was saying vertical this way. So not actually vertical. In my diagram, this is horizontal direction, but that is with respect to our vertical, okay? But in this rocket ship, the vertical will be that direction over there. Isn't it?
yes, sir.
That is what I was talking about. In fact, I was saying that there is no experiment that can be conducted which can differentiate between a uniform acceleration and a uniform gravity in the opposite direction. They are in fact known as the principle of equivalence actually. Any kind of uniform acceleration is equivalent to a gravity in the opposite direction in that particular reference frame, in fact. Okay. Shivankar, you have made a mistake, as you could see now. You have just assumed that they are indeed meeting somewhere, and then what you've done 4 minus x equal to the entire thing. There's a mistake in that case. Okay, is okay. Now, who was that? Rahul, your question, we shall do it after some time once you've taken some projectile. Okay. Let's talk about the projectile itself. In effect, we are going to deal with motion which takes place in two directions, and two dimensions, basically in a plane.
Sir,
Huh?
sir, but I have another doubt in this question only.
What?
Sir, sir, if sir, it is written in the question that it is moving in a gravity-free space.
Yeah.
Therefore, there is no means projectile motion for both the particles.
Yeah.
So they are moving. So can we find out the relative motions between them? Means can we equate the relative velocity and then we can divide it by the distance between the two particles with the relative velocity, and can we get that time?
That can be done, but the question is the relative acceleration will not be zero throughout. Okay, the point in this case is that as we saw just now, the second this particle from the left side, it comes to rest only within 0.3 seconds. So during those 0.3 seconds, the relative motion, the relative acceleration rather, is zero, which implies for those 0.3 seconds, the relative velocity is nothing but 0.5 meter per second. But after that, what happens? After that, the first particle actually is at rest with respect to the rocket. So it has actually an acceleration of the rocket itself. Say it is not moving with respect to rocket actually, but the other particle is moving. So in that case, the relative acceleration is no longer zero actually, isn't it?
Yes,
That is
sir.
why
At
you
that
can't.
time, particle A will face zero acceleration.
Yes, with respect to rocket actually.
Yes, sir.
Okay, that is why you can't apply that idea of relative motion. You could have done that if for example, I throw something in uniform gravity. The acceleration was always there. If it was always there, then you could do this. Say if I just project two objects simultaneously, for example, I just throw two objects simultaneously upwards, one with a velocity of 4 meters per second and the other with a velocity of 3 meters per second. In that case, the motion between them is going to simply be that of a relative velocity, which is 1 meter per second actually, because they are both moving in the same gravitational field. So as long as they are both in air, as long as they are both in motion, the relative velocity is going to be constant. But once one of the particles struck the surface, or it has just reached the earth over there, then the motion is no longer the same actually, relative. Okay, then the uniformity of the relative motion is not there then. Fine. Okay. I was saying that when we deal with projectile, effectively projectile motion is an example of a two-dimensional motion where the motion takes or is confined in a single plane. That plane usually be the vertical plane. I mean, so the vertical with respect to gravity essentially. Mostly the idea is that once you've thrown some object, Anik, what happened? Which question? Yes, I will talk about this question once I do done with the projectile, by the way. What is your question? At least let me check it out. If it can be done without projectile, we can do it. 13th one you said. Well, there are so many questions, by the way. Can you specify which one of them is there? Anik? 13th. Okay. 13, 11 and 13. 13 is this. Achha, this cabin is moving. Yes, it will be useful if I do it. However, this is not very difficult, by the way. It turns out in this. Done that.
So I have done
Achha.
uploaded in the group. Yes,
So,
sir.
Anik, Ankit said that he has done it. Achha, getting different answers. Okay, I'll just do that after the class. Okay, after the theory part, I've just done it. I'll do that. Okay. Yes, Ankit answers 4, but answer given is 8. Okay, fine. I'll check it out after the theory part. Fine. Okay. Now, yes, the usual idea that when we just deal with projectile motion or any kind of two-dimensional motion effectively, it is useful to take up in this case a coordinate system, which is usually, if I talk about the projectile which is projected near the Earth's surface from the ground essentially, then we can take up the x-axis as the horizontal and the y-axis vertical. In this reference or this coordinate system that we have chosen, we could, resolve the gravity, the acceleration in this case, one acceleration along the y direction. Along the x-axis, there is no acceleration simply. Before that, I just forgot to tell you what a projectile exactly is. Effectively, when you just throw something, yes, Shubhankar, I'm starting projectile. It has to, I'm just talking about projectile for so long. Anyway, the point is that when I throw something near the Earth's surface and it moves without the effect, any external influence apart from gravity, implying we can just neglect the air resistance. The point is when it is moving freely with respect to the Earth, in the gravitational field alone, there is no other influence. Then we have motion of projectile effectively. Obviously, in a real life situation, the air will be there. There will be some air resistance present. Even then, it is a projectile method. But at least for our analysis, we shall neglect that air resistance part. It simply is too complicated to begin with, and it is not worth the effort over there for the moment. Later on, we might include that if you want. So the idea is that we shall imagine that a particle is projected from the Earth's surface at some point, and it is moving freely without any other influence, without any influence of the air, for example. Now the projection point I'm going to take up as O and call it the origin itself. That is the simplest possible situation. We choose the x-axis to be running parallel to the ground, and the y-axis is in fact perpendicular. Strictly speaking, in this case, we are assuming the motion to take place entirely on the xy plane, which is coincident with the vertical plane. Actually, at any point, if we just throw the object, then the plane which contains the path of the object and the vertical is the plane I'm talking about in this case. However, again, you would notice that in this case, we are neglecting the effect of the rotation of the Earth. Actually, it turns out in real life situation, when the projectiles are having long range, the rotation of the Earth can also come into picture. Okay, that I'm again for the moment neglecting. We're simply considering that the motion is confined to one single plane. That is, in this case, the xy plane, which is nothing but the vertical plane at that particular location. Now, in this case, we assume that the particle has been projected with a certain initial speed, which I'm going to call as u, and it is projected at an angle, which is alpha, with respect to the horizontal. Well, Rahul, if you do include the air resistance, then it creates a problem because the air resistance actually is opposite the direction of velocity. So it will have both the components which will change because the velocity is changing. Direction for the air resistance will also be changing because the velocity in this case will obviously go that way. So the air resistance always acts opposite the velocity. So that will be an example of a non-constant acceleration in both directions actually. In fact, we shall have acceleration in the two directions where the acceleration depends on the velocity in fact. Okay. Right now we're neglecting that. We are simply assuming only one gravity, gravity vertical downward, so there is no acceleration along the x-axis. You see, there is very any vector. In fact, you can resolve vectors along any directions, and as it turns out, as we have seen earlier in case of that relative motion example as well, the triangle problem we did, I said that in the direction, in any given direction, the displacement was determined by the velocity in that direction. In a similar fashion, in any direction, the change in velocity will be determined by the acceleration in that direction. So, for example, in this case, if I just consider the acceleration, there only one acceleration, which is g along the vertical direction, along the y-axis. There is no acceleration along the x-axis. As such, the velocity along the x-axis cannot be affected by the acceleration in the y direction. That's always true, by the way. The velocity along a certain direction will not be affected by mutually, affected in the sense that it will not be changed. So the velocity in one direction cannot be changed by an acceleration in a mutually perpendicular direction. In fact, you could prove this that whenever it happens that the acceleration is always perpendicular to the velocity, in that case, the speed remains constant, in fact. Okay. Anyway, we shall come back to that part a bit later. For the moment, let me write down the equation. The point is that this is an example of uniform motion in x-axis because there is no acceleration. In y-axis, it is again a uniform acceleration motion. So we can apply all the equation that we know for the uniform acceleration along the y-axis and all the equation that we know for uniform motion, which implies a constant speed motion along the x-axis. So it makes rather simple because we can break up the motion into two mutually perpendicular directions and deal with them separately as if the other one is simply not present. In fact, if you throw this object at an angle and then you start running with the same horizontal velocity or same velocity which this particle has in the horizontal direction, if you just throw the object at an angle alpha with a speed u and start running with a speed which is u cos alpha, say the same which has this particle in the horizontal direction, then with respect to u, the particle actually will simply seem to go up and come down. There is no horizontal motion at all. What I was saying, Shubhankar, in this case is that if we consider in this case, what I was saying is the good thing about this particular situation is, or in fact, any kind of two-dimensional motion or three-dimensional over there, what happens is if you can always deal with the motion by looking at the two components separately, as if the other one was not present. So if I just look at the motion along the x-axis, I can simply forget about the motion along the y direction. And if I look at the motion along the y direction, I can simply forget the motion along the x-axis. Quite obviously, they're connected because the time is the same over there. But apart from there, they can be dealt entirely independently of each other. Okay. The only parameter which relates them is a time parameter. Okay. So what I was saying in this case is, in fact, that if you just throw the particle from the ground at an angle alpha at a speed u and start running below the underground with a speed which is u cos alpha, you shall find that the particle simply goes up and comes down. That is what the path is going to be actually. In this case, obviously, the path is going to be something like this. We stand on the ground and look at the object, the path will be something like this that we know by experience. But if we just start running below the, with the same speed on the ground, which is equal to the horizontal speed of this object, in that case, you will see that the object no longer actually goes in path like this. In fact, it goes vertically up and comes down. You might have seen movies, for example, where, for example, from a bomber plane, bombs are dropped in war movies, for example. In that case, if you look closely, you'll find that the bomb, they simply go down vertical before leaving behind over there, okay? I mean, say from the perspective of the rocket, or sorry, from the aeroplane, if the, I mean, say a picture of the bomb is taken, which was dropped essentially by the aeroplane, it will seem to go first vertically down, then it will just lag behind. With respect to the ground, on the other hand, some other picture is going to be seen. If you're standing on the ground and a bomber plane flying this way releases a bomb, it will actually go on a path like this. But with respect to the aeroplane, the path seems entirely different. It will happen always, therefore the path will depend on the choice of the reference frame. Fine. In our case, the reference frame is simply the ground. We're standing on the ground, looking at the object which has been thrown with a speed u at an angle alpha with respect to the horizontal. As I was saying, in this case, we can treat the motion as two separate motion, one along the x-axis and one on the y-axis. The relating parameter being the time in both the cases. Time will be same, but everything else can be dealt with independently to each other. So if I resolve first of the initial velocity, I can just draw perpendicular. I find in this case that this part becomes u cos alpha. That is the initial horizontal velocity, and this particular component becomes u sine alpha. That becomes the initial vertical velocity. What can I explain with the help of a diagram, Shubhankar? The path of an the bomb that you have to see actually with respect to in the movies. You can see that I cannot just draw a diagram right now. I can draw effectively. The point is when the bomber is over here, for example, and it is moving in this direction. So when the bomb is released, it will be actually having a velocity of the bomber itself. So when the bomb is released, for example, its initial velocity will be also horizontal. Okay. So what happens is it is moving, I mean, say in two directions simultaneously. It is also moving forward, but it's also going down as well. That is why the two motions combined goes forward, but additional goes down as well. So it just keep on going like this. This is what we shall see in case of a bomber over there. Fine. In fact, you might kind of trying to consider, for example, if you go in a train, for instance, if you're moving in a train which is traveling with roughly uniform speed over there, it is a projectile, by the way, Onik. It is not a half projectile. It is not inertia either. The fact is that when you just drop a train, so I mean, say you're just traveling in a train, you just take up some object and drop it outside the window. Obviously, if it is a small object like a wrapper, for example, it will just fly off in the wind. But if it's a bit dense object like a stone, you can actually see the stone falling just beside you, in fact. U is the resultant of two vectors? No, U is the initial speed. Actually, initial speed in this direction, I have resolved that speed in two components. One is the horizontal, the other is the vertical. So U is not the resultant, but rather the components of U are these two quantities. So you might say that is same thing over there. Okay, u cos alpha is the initial horizontal speed. As I was saying, or you can think of them like shadows over there. Okay, projections. You just shine light on them. It just goes. The shadow is this way. That is the. In fact, the two motion that you can consider on the two axes, they can be thought of as shadows. If I shine light on, for example, from the top, then the shadow will just move around the x-axis, and that is the x component of the projectile over there. And if I just shine light on this from this side, the shadow will move in the y-axis, and that will be nothing but the vertical motion itself, which we can consider as I mean, say just like as if a particle was thrown upwards simply. So in this case, as the important idea you must remember over here is the fact that the two components can be dealt with separately. So I can simply write down the equation along the x-axis and the y-axis as if the other was not present. In this case, for example, if I consider the initial velocity along the x-axis, okay, first of all, the acceleration along the x-axis, which is pointing towards the right, the acceleration is 0, and along the y direction, the acceleration is equal to minus g. Why minus g? Because my y-axis runs upward and g is pointing downwards. That is why the acceleration along the y-axis is in fact negative. Fine. And next we have for the velocities, the x velocity, because the acceleration along the x-axis is simply 0, the x velocity will simply be a constant. So therefore, Vx is turning out to be simply u cos alpha for all times. Nothing but u cos alpha. So the x velocity is simply a constant. It just travels the uniform speed u cos alpha along the x-axis. On the other hand, if I look at the y velocity will be as if we have thrown something or an object vertically upward with a speed of u sine alpha. Okay. The x motion will have no bearing on the y coordinate, y motion. So Vy is affected by gravity because gravity is pointing downwards. So Vy will change, and I can apply the usual formula of the uniform acceleration motion. We will have those results b equal to u plus at, s equal to ut plus half at square. Those formulas that I can apply in this case in the y direction. Okay. So for the y direction, we end up getting Vy as the initial y velocity, which is u sine alpha, minus gt. Why? Because there is an acceleration along the y direction, which is equal to minus g. Therefore, the relevant equation along the y direction becomes this for the velocity. The y velocity is nothing but u sine alpha minus gt. So these are the velocities. Fine. Next, we just talk about displacements. You see the displacements again, we can apply the same idea along the x-axis. The displacement will be given by simply u cos alpha into time because the x velocity is a constant. Along the y direction, because there's a uniform acceleration downwards, we can apply the formula ut plus half at square. Only the fact is that in this case, instead of distance, it will give us a displacement. So if I look at the x and the y motion, I have x as simply u cos alpha into t. That is, technically it's a displacement, by the way. In this case, it's actually a displacement, delta x. But the fact is, it was already starting from the origin, and that is why displacement and the position are the same thing. So anyway, first let us write out displacement. Displacement along the x-axis becomes this one. Along the y direction, we have to apply ut plus half at square. So I get in this case u sine alpha into t minus half gt square. That becomes delta y, which implies a displacement along the y direction. Now these are displacements, by the way, which implies the change in position with respect to the initial one. In our case, it was projected from the origin itself, which implies the initial position is 0 in both cases, and therefore a displacement is same thing as the position. You remember that the displacement is a change in the position coordinate. In this case, because the initial position coordinate is 0, therefore a displacement will be same thing as the positions. Therefore, I could write down finally the x coordinate of the object simply as delta x, which is u cos alpha into the time, and the y coordinate as u sine alpha into t minus half gt square. These also become the position because the initial position is 0. Yes, the initial coordinate is 0, 0 actually. It's starting from the origin itself. That is why the displacement and the positions are the same thing actually. These equation therefore can give us the position of the object at any given time t, obviously as long as it does not hit the ground. There's just one more thing you should notice. Oh, bigger. Okay, fine. Now, are you able to read all these things by the way or no so far?
No,
Sir,
sir.
you written last y equals to u sine alpha into t minus half gt square.
Yes, yes. Okay, Devjyoti, you can't read it. Acha, let me see. I'll just
Write
take
little
the-
bit bigger.
Okay, fine. I'll write a little bit bigger from the next time, but at least these parts I can send you a picture.
Yes, sir.
Sir, I'm sending.
ठीक है, Ankit, do that. Take a snapshot and send it. Okay. ठीक है, I'll write bigger again.
Sir, when I'm going to zoom it, the screen becoming white.
White. I can
Yes,
zoom
sir.
it. Yes, I can also zoom it by the way. Okay, my screen is not becoming white. It is okay. Anyway, ठीक है, no problem. I'll just add bigger next time. However, what I was saying, one thing that you should keep in mind, what you can do in many cases as well, is when, for example, the initial position is not the origin, for instance. It may happen that you have chosen the origin at some other point, for example, not at the point of projection, but some other point. Maybe you have, or you can just say that the origin is over here itself, but the projection point has shifted. So now let's throw it from here. From this point, you just throw it that way over there. In that case, what happens is the initial position will change. For example, if I just throw it from a location which is x0, y0, which is not 0, I just throw it from a certain point over here, which is x0, y0. In that case, so far these equations remain the same. Displacements will be same. What will change is the position, because then the displacement will become x minus x0 actually. If I throw it from a certain point over here, which is at say x0, y0 in this direction, in that case, what will happen is the displacements equation will still remain the same. In fact, all these three equations are the same. What will change is the final position. The position will basically be obtained by adding displacements to x0 and y0. Okay, that's the only difference that we should have. In any case, we shall come to that after some time. For the moment, stick to this particular situation where the point of projection is at the origin itself. Okay, once we have got the position coordinate, which was x equal to u cos alpha t and y equal to u sin alpha t minus half gt square. There are actually many usefulness of using the coordinates, for example. For instance, as I know that the time parameter is same in both the equations, so I can actually eliminate the time parameter and get an equation which relates y and x over there. That will be nothing but the equation, the path that the object takes in the xy plane. If I do that, for instance, you notice that since the x coordinate was u cos alpha into t and the y coordinate is u sin alpha t minus half gt square. These are two equations. Yes, exactly. I can first find the, say for example, I just find t from the first equation and put that t in the second equation. Because time is the same in both the cases, therefore I can eliminate t to obtain, I say eliminate eliminate t to obtain the equation of the trajectory or the path, basically. The equation of the trajectory as you could, say, basically the idea is to just put the value of t from this first equation into the second one, and that upon simplification will give us something like y equal to x tan alpha
minus gx square divided by 2u square sec square theta.
yes
Or alpha.
minus gx square divided by twice u square cos square alpha. That becomes the equation of the trajectory. Okay, this is actually obtained by eliminating the time from the first equation and the second one. I just find the t from the first equation, put in the second one, and simplify it up. We end up getting in this case the equation of the path or the trajectory as y equal to x tan alpha minus gx square by twice
So
u
we have
square.
found that y equal to x tan x 1 minus x over r.
What x?
X tan alpha 1 minus x by r.
Yeah, that
I
you could
have
write
written
down,
in the chat.
but I haven't yet gone to the range, so I'll just do it a bit wrong. But yes, you could do that. The chat is suspended. Anushka said something from high to from update downwards. Well, Anushka, you can just consider it any one. You can always deal with that in both situations. It depends on what choice you have, what you do it. And it can be taken in both ways. Anyway, this is first of all the trajectory. Now we can actually do something else. For example, if this is technically speaking an equation of a parabola, by the way. It's a quadratic in x. So this is an equation of parabola. There's a downward opening parabola, in fact. It turns out the shape looks like, in this case, we already know how a parabola looks like, by the way. It has a symmetrical, it looks in this case, in this fashion, that we have also seen by experience. It's strictly speaking a parabola which is like this, but only require that part which is above the x-axis. I can find, for example, from this equation we have got, the time of flight, for instance. I could just consider how long it takes for the particle to return back to the same horizontal level. If I find the time of flight or the time it takes the particle to reach its original horizontal plane, then I could obtain this by putting y equal to 0 in that equation of that equation you have got for the y as a function of t, because when it returns back to the ground level, we notice that the y coordinate again becomes 0. If I equate the y coordinate to 0, obviously it will give us those instants at which the y coordinate is 0. So one of them is already the initial point, which will, if I equate y equal to 0, that gives us u sine alpha t minus half gt square equal to 0. I can factorize t in this case. Yes, Anushka, that is correct. I can factorize t and end up getting u sine alpha minus gt by 2 equal to 0. But obviously, one of the roots in this case is t equal to 0, which is nothing but the initial moment. That because at that point also it was at y equal to 0. The other root is going to therefore give us a time of flight. So that is the time given, time which is going to be obtained at this location over there. Fine. So I can just solve this one over there to get therefore the time of flight Remember, this is the time of flight above the horizontal plane actually. Obviously, if there's a ditch, for example, say, for example, there's a ditch that way, then the time is going to be more. In that case, I can't apply this formula for time of flight, but this is only the time of flight above that horizontal plane. Okay. So time of flight above the horizontal plane, which I'm not writing, is given by, from this equation, twice u sine alpha divided by g. I simply equate the second factor to 0 and solve for t. That gives us twice u sine alpha upon g. I can also obtain the same equation in a different way. I could figure out, for example, the time at which it reaches the highest position. Now, if you look at, in this case, the two components of the velocities, the velocity along the x-axis remains a constant. It does not changes. But what about the velocity on the y-axis, by the way? You notice that as a particle moves ahead, the y velocity keeps on actually decreasing. The x velocity is always the same. The x velocity is initially, for example, u cos alpha, this much, this point also this much, u cos alpha, u cos alpha, u cos alpha, your same length supposedly. The x velocity remains the same at all particles location. At every point, the x motion is unchanged. It remains the same. All the vectors are equal length. Okay. On the other hand, what about the y velocity? The y velocity is actually reducing because of the equation that Vy is u sine alpha minus gt. So it reduces uniformly. Initially, it was u sine alpha, for example. In that case, then it becomes a bit lesser, then a bit lesser, then a bit smaller, then becomes completely zero at the highest point actually. Then it starts increasing in the negative direction more and ultimately becomes more as well. There is a situation for the y velocity. The y velocity is not understood this part. Well, you go back and look at the equation for Vy, Shubhankar. Vy was given as u sine alpha minus gt, which implies as time passes by, u sine alpha minus gt decreases first. So it actually always decreases. We're always subtracting something from u sine alpha. U sine alpha is fixed and subtract gt, but gt is increasing as time passes by. The arrow part, I have just drawn the vertical velocity. The arrow part, the red one is the horizontal velocity, which remains the same always because the x component never changes. The y component, however, the velocity will keep on reducing. Why? Because there is an axle retardation rather than that direction, or acceleration in the negative direction. So initially, the arrow was big, then it becomes a bit lesser because they have subtracted gt part. As time passes by, more and more is subtracted. That is why these vectors, they keep on getting smaller. At some point of time, they become zero, the length. That will be the point when it will be at the highest position. Because before that moment, there was always a velocity in the upward direction, therefore it will always increase by. But by the time it reaches zero velocity at that point, along the y direction, the height must be there for the maximum. Subsequently, Vy becomes negative, so y again start decreasing. Okay. So if I just consider the time at which the y velocity becomes zero, double of that time will also be the time of flight actually. Why? Because the motion is symmetric under the gravity. Therefore, whatever time it takes to go up must be also time taken to go down. And to go up, we can find a time by using the fact that the highest position that we have, the y velocity is zero. And that implies u sine alpha minus gt is equal to 0. That gives the time as u sine alpha by g. So double of that becomes twice u sine alpha upon g. The vertical velocity, Avibrata, if you just look at the equation that we wrote earlier, we wrote down Vy is equal to u sine alpha minus gt. That is what I wrote down earlier. Okay. Which implies what? We notice that u sine alpha is a constant number. U is the initial speed, alpha is the angle of projection. So they are fixed values. But yeah, that's okay. This one is effectively always we are subtracting gt. Now, as time increases, gt is also increasing. So we are subtracting more and more quantity from u sin alpha. Therefore, Vy, which is u sin alpha minus gt, keeps on decreasing. That is what I've shown. As time passes by, the particle also goes ahead. It goes up as well. At the same time, Vy becomes shorter and shorter and shorter, and ultimately, at some point of time, will become zero. That point is when the particle reaches the highest position. Because before that, Vy was always positive. Therefore, y must have been increasing. Only at the point when Vy becomes zero will y becomes the maximum. And therefore, I can find out in this case the time to reach over there by using the fact that that point of Vy is zero. And so we get 0 equal to u sine alpha minus gt. This t will be therefore turning out to be u sine alpha upon g, and because the motion under gravity is symmetrical, whatever time it takes to go from here to here must be time taken from here to ground again. That is why time of flight becomes twice of this value, which is giving us t equal to u sine alpha upon g. So just take it twice of this one, which is nothing but this one. That is our time of flight in this case. Yes, Ankit, u cos theta remains a constant, u cos alpha rather. The x velocity basically, it remains the same because there is no acceleration in that direction. Because on the x-axis there is no acceleration, therefore Vx cannot change. That is why this vector this x component always remains the same, which implies the highest point, the speed is not zero, but rather the speed I am saying, the speed is in fact equal to the x component of velocity as well. The highest point, therefore, the speed is nothing but u cos alpha, okay, which is the minimum speed it can have. The speed is reached over there, which is u cos alpha. At every other point, u cos alpha is going to be different. It will change in the projectile on the inclined plane. Yes, definitely, Ankit. If you take a projectile on the inclined plane, then obviously Vx and Vy both will change, okay? But in this case, at least it is not so, because in this case, the x acceleration is simply not there. That is why it is not changing the x velocity. Fine. Anyway, so we have figured out in this case the time of flight. The projectile is always symmetric at the highest part. Well, actually, if it is on a horizontal plane, then in fact, if I was saying, for example, if I throw it, for example, at top of a tower, for instance, yeah, the path, the total part is okay. Total part is always going to be symmetrical. But if I throw it from the top of a tower, for instance, then we don't have a complete parabola. In fact, or at least we have only part of it. Throw it from a tower, for example, it goes like this. So in this case, obviously, about the highest it is not symmetrical. But it will be if I extend in the backward direction of it, right? So in that sense, it is symmetrical. Yes, I mean, say if the motion is complete from one horizontal, I mean, if it's complete above a horizontal plane, then if I just consider any horizontal plane above that, whatever the motion is, that is going to be symmetrical. For example, even in this case, above this horizontal plane, the motion is symmetric actually. Okay. Anyway, finally, we can figure out what is the horizontal range of the projectile and the maximum height as well. Maximum height can be easily done. I can just use the fact that when it reaches the maximum height, the vertical velocity is zero. So I can use the third equation of kinematics, v square equal to u square plus twice as that one. Use the fact that when it reaches the highest location, which is quite obviously where the velocity is zero, the y velocity is zero. So I notice in this case that at the highest point, Vy is equal to 0. So that gives us initial y velocity, which is u sine alpha whole square minus twice g capital H, that must be 0. We get u square, I mean, v 0 equal to u square minus twice gh effectively. So that will give us the height of the projectile, the maximum height rather, as u square sine square alpha upon g. That becomes therefore the maximum height attained by the projectile above the horizontal surface actually. That is the maximum height attained by the projectile above the horizontal surface. Okay, if the line is tilted anyway. And if I look at the range in this case, the horizontal range of the projectile is this distance, this one. The distance from the point of projection to the point where the object strikes the ground once again. That becomes the horizontal range on the horizontal plane actually. Obviously, if I take a different plane, like for example, I take a plane like this, then the range on that plane will be different. But at least for horizontal range, implying the distance on the horizontal at which the particle comes back after being projected, that can be obtained by looking at a displacement around the x-axis by the time it returns back to the ground. The range, therefore, the horizontal range is nothing but the displacement along the x-axis by the time the particle returns back to the ground. So the time taken to return back to the ground is nothing but a time of flight, which I wrote in earlier, twice u sine alpha by g. And therefore the range will be turning out to be simply u cos alpha into that time, because the horizontal velocity remains the same. So the horizontal range to the point of projection So the horizontal range, I consider, will be simply the displacement along the x-axis. Okay, again my chart is frozen by the way. Rahul, what I've said, rocket which experiences an acceleration upward, then should. Rahul, if it is placed on a rocket which is experiencing acceleration upward with an acceleration ay, then quite obviously the acceleration of the particle also becomes ay, isn't it? It will not be between g and, I mean, say, I hope you're talking about the rocket itself. No, Anik, that is not exactly what we have. Okay, you are talking about an elevator. Yes, you could think of it that way. I mean, say, with respect to ground, it will be however. With respect to the rocket, it will be there, however. With respect to ground, I mean, say, if we throw the rocket, object from the rocket outside, then obviously it will be nothing but g itself, the acceleration. But yes, with respect to the rocket, things will be different. I mean, say for example that you are, there's an elevator which is either accelerating upwards or downwards. With respect to the elevator, the acceleration will be different, it won't be g. But with respect to ground, it will be still the same, g. Yes, Shubhankar, what you said is correct. But it won't be a constant speed in the direction of projection. It will be along the horizontal direction, actually. Okay. The horizontal range, therefore, turns out to be nothing but the x displacement during the time of flight. So it has to be, therefore, u cos alpha into the time of flight. I can just plug the value of t, which is nothing but twice u sine alpha by g. So I end up getting twice u square sine alpha cos alpha upon g. That becomes the range for the horizontal range, actually. Okay, the line is already tilted. Twice u square sine alpha cos alpha upon g. That is what we have in this case as the formula for the range in the horizontal plane, actually. This can be written down a number of ways. For example, I can utilize the trigonometric identity for the line always becomes tilted by the way. This is a perspective problem that we have. So the range in this case is, therefore, this is the horizontal range I said already. Twice u square sine alpha cos alpha by g, which I can write down in a number of ways. For example, I could utilize the trigonometric identity. The twice sine alpha cos alpha is nothing but sine 2 alpha. So that this can be written down in a shorter form as u square into sine of 2 alpha divided by g. That is also the expression for the range. From here we can just look at a couple of things. For instance, because sine of an angle cannot be more than 1, therefore the maximum possible range that we can expect on a horizontal plane when I can change the angle of projection at the same speed u is turning out to be therefore u square by g, because then sine 2 alpha will become 1 for 2 alpha equal to 90 degrees and alpha equal to 45 degrees. Therefore, the range on the horizontal plane has a maximum value for a certain speed of projection as u square upon g itself. We throw a projectile at various angles but the same speed, then the range becomes maximum equal to u square by g, and that happens when the angle of projection is equal to 45 degrees. Okay, I just can therefore see that the maximum possible range R max is u square by g. I mean, for a given projection speed, actually, I'm assuming that the speed of projection remain the same, but I can just vary the the angle to get different ranges. And we notice therefore that max is u square by g. It happens when the angle of projection is 45 degrees actually, when alpha is pi by 4. So when the projectile is launched at 45 degrees, then it is going to attain the maximum range. Apart from there, you can also see in this case that the range can be also written down. The range is same thing as u squared by g, and I could write down sine of pi minus 2 alpha. Sine theta is same thing as sine of 180 minus theta, and then I can just take in this case sine of, I can pull out 2 common, I get pi by 2 minus alpha, which I could write as a sine of 2 beta, for example. This becomes, it is visible, u square upon g into sine 2 beta, where beta is equal to pi by 2 minus alpha, which implies therefore where beta is equal to pi by 2 minus alpha, which means therefore that if I throw the projectile with the same speed u but at angle alpha and pi by 2 minus alpha, in both cases the ranges are going to be exactly the same. So for example, if I throw at an angle alpha with respect to the horizontal, say for example, which is this one, alpha with respect to horizontal, and I throw another particle what is saying, Ishant, can click a pic of the board. Oh, acha. Okay, let me finish this diagram, then I'll just send a picture, okay? In this case, I was saying that for an angle alpha, okay, the conclusion is that for 2 angles alpha and the corresponding complementary angle 90 minus alpha, the ranges are equal actually. So we have one of the projectiles at angle alpha, the other one is actually 90 minus alpha, that will be this big, for example. The speeds are equal, both the speeds are the same. In that case, the ranges are going to be same as well. This will be something like this, and this will be something like this. The ranges are going to be equal actually, but the other parameters are not. The time of flight will be different. The maximum heights will be different, but what is not different is the horizontal range. That remains the same actually. So it is again the picture. It is rotated because the picture has been rotated, but unless somebody else has not sent it yet, there it is. Oh, my network is too slow, it seems.
So did you already send?
Yes, just now I sent it.
Okay, sir.
Okay. You also notice in this case that these two angles, alpha and 90 minus alpha, they are equally inclined to the direction of the maximum range. The maximum range is 45 degrees. The maximum range is at 45 degrees, which is nothing but the bisector between the two directions. And these two directions are equally inclined. These two directions are equally inclined to the 45 degrees angle. And if you throw it 45 degree, then the range is going to be the maximum possible, something like that. The range is maximum at 45 degrees, but as long as we choose directions which are equally inclined with respect to the maximum range direction, the two ranges are turning out to be the same. Okay, ranges are going to be equal as long as those directions are equally inclined to the maximum range direction, which is nothing but 45 degrees. Then in that case, the ranges are remaining the same actually. Okay, so we have basically formula for a range. Last part I said that if the angle of projection is equally inclined with respect to the maximum range angle, which is 45 degrees, the maximum range angle is 45 degrees. Therefore, as long as the projection directions are equally inclined with respect to the maximum range direction, the ranges of the projectiles will be equal. That is what I said. Meaning that it's simple enough. It says if you just throw projectiles which are forming equal angles with respect to 45 degree into two directions, one is above 45, the other is below 45, the same speed, then the ranges are going to be equal. And both these directions are actually complementary angles. If one of the projection angle is alpha, the other one becomes 90 minus alpha actually. Okay. Do the ranges? Yes, that is what happens, Avibrata, because initially, I mean, the range will be greatest at 45 degrees. So once we exceed that angle, the ranges start decreasing again. In fact, you can see that when I just have very steep angle, like 80 degree, for example, this goes up and then comes down. So range is quite small over there, isn't it? So it has to be decreasing. Yes, definitely. Okay. Right. Apart from there, we can do some more things by the way. So far, we have looked at the range and the maximum height. If we now go back and look at the formula for the trajectory that we had, the equation for a trajectory that was turning out to be the equation of trajectory that was y equal to x into tan alpha minus gx square divided by twice u square cos square alpha. That was the trajectory equation actually. Yes, on it, that is fine. Okay, now we see in this case that if yeah, that's fine. You can just write down entire thing in terms of the ranges actually. What is g by u square x square? What is that? I can just pull out in this case, for instance, I mean, tan alpha is sine upon cos actually. I might in this case pull out tan alpha common and x as well. So I get x tan alpha common. What is left is 1 minus g into x divided by twice u square. I have tan alpha, I have pulled out common, so I must divide with tan alpha, but then it becomes sine alpha into cos alpha. Sine alpha into cos alpha is what I have. That is, once I have pulled out x tan alpha common, I end up getting in this case Anushka, what are you saying in this case? Previous message reach. What was the previous message, Anik? You have written 45 plus theta and 45 minus theta. And you're saying y equal to g by twice u square into x square. I'm not getting it. Anushka, can you? Yes, Anik, it reached. It's not reached. Anushka, can you repeat what you were saying? Oh, interesting. Okay, you were writing the equation of trajectory. That was not, yeah, you actually made a mistake in this case.
So there,
Huh?
so there are two equations for trajectory motions.
No, the same equation. There's only one equation. I mean, as far as we stick to the projectiles above horizontal plane, the equation of projectile trajectory is this: y equal to x tan alpha minus gx square by twice u square cos square alpha. But you can rewrite down in different ways. Okay, you can write down in different way. For instance, if I consider in this case pulling out x tan alpha common, in that case, what is left over here is one of the x is gone. I pulled it out of common, and tan alpha we have taken out common, so I must divide with tan alpha in this case. But tan alpha is sine by cos, so one of the cos gets cancelled out. I end up getting gx by twice u square sine alpha cos alpha. But then 2u square sine alpha cos alpha by g is a range. This can be therefore written down as y equal to x tan alpha. That will be just easier to remember, that's all. 1 minus x upon the range. That way you could write it down. So in this way it will be easier to remember, in fact. Okay. So that is the equation of trajectory now in terms of the range over there. Okay. We have taken up the range, we have taken up the maximum height over the horizontal plane, we've taken the time of flight as well. Obviously, as long as the projectile is projected from the ground and we take that point as the origin, all these things are going to be valid. But if there's a difference compared to that, for example, there's nothing that we want to write now. Shubhankar, well, yes, there's a couple of things. For example, I might see how the speed of the projectile changes with respect to the height. Okay, if I consider the speed of the projectile as a function of height, the height implies in this case the y coordinate I was talking about over there. But say, for example, that I projected a projectile, thrown something from the ground at a speed u angle alpha, and the path is like this. So I just take up some point which is at a height h from the ground, small h. The height from the ground is small h. At this particular point, if I figure out, for instance, the speed of the object, what will be that? How to figure the speed at this particular point? First of all, the velocity. The velocity is obviously tangent to the path, like this. It will be a bit less compared to u. You'll have two components. One will be the horizontal component, the other one, the vertical component. It's quite obvious that the horizontal component is nothing but u cos alpha. That is the same. In this case, if I just consider the horizontal component at a height h, the x velocity that will be the same, the u cos alpha, because there is no acceleration on the x-axis. But in the y direction, what do we get? Well, because we want in this case the speed as a function of h actually, there's no point in writing down. And this is not a curved line, but it's a straight line over there. This is the vertical velocity, in fact. looks curved. It's not an arc. It's a straight line. Because we're looking in this case the speed as a function of h, it is therefore useful to write down the y velocity also as a function of h. For that case, we can utilize the equation that v square equal to u square minus 2gh. To write down in this case vy square equal to the initial velocity along the y direction, which is u sine alpha, whole square minus 2gh. That becomes the vertical velocity squared at a height h. Now the speed at this particular point, therefore the speed at height h, the speed at height h, which is this one, I'm just putting a v, that can be obtained as root over of the vx square plus vy square. That is what I have. That is the speed at a certain height h over there. Speed at height h is what I'm evaluating. Okay. So if I now plug the value of Vx and Vy, Vx is square becomes u square cos square alpha. Vy square is u square sin square alpha minus 2gh. If I add them up, I get u square cos square alpha plus u square sin square alpha, which is nothing but u square minus 2gh is what I get. This becomes therefore root over of u square minus 2gh. That is therefore the speed at a certain height h. It obviously could have been obtained much easily if you apply the energy conservation, for example, but we haven't yet formally done it, so I'm not writing it down that one. Okay, we just utilize the kinematical equation to obtain the speed at a certain height h as u square. Again, you could see in this case that as the height increases, the speed reduces. Okay, till it reaches the maximum height, and it is u square minus 2gh. Again, let me click up a picture and send it over there.
Sir, kinetic energy doesn't depend upon direction, no?
Kinetic energy
Doesn't depend upon any direction.
No,
Sir.
no. Energy has no direction. Energy is scalar quantity.
So I'm sending a pic.
I have clicked it. If you anyway, okay. I already clicked it by the way. So if you okay, fine. Oh, so how have they already done that? Interesting. You done much faster than me. You take a snapshot and send it in it. That's fine. I will take a picture and then send it, so that will take some time. Okay, fine. So that is the height. Subankar, can you see now? Yes, 2 pics. You can delete. Oh, okay, I can delete. Okay, fine. Leave it by the matter.
Yes, sir, done.
Okay, fine. And what about the angle, by the way? Can you figure out the angle as a function of the height, or the angle which the velocity forms with respect to the horizontal? It's called this angle theta. So how will theta change with respect to height, by the way? It's quite obvious that we can see as height increases, the angle theta first of all decreases. It becomes 0. Yes, h direction v is constant actually. This vector always remains the same. This one basically decreases, so the angle will also reduce. Gradually it becomes 0 and then it becomes negative as well. Because what about tan theta, by the way? Can you find tan theta as a function of height h? Tan theta as a function of height h.
Sir, root over of u sine alpha square minus 2gh divided by u cos alpha.
I mean, say u cos alpha is outside the square root, isn't it?
Yes, yes, sir.
That is the same thing. You can just take it inside and you can get, for example, root over of tan alpha minus something. H is already the height at any point over there. Height is, in this case, h is the height at any arbitrary moment. Yes, random height, exactly. Okay, got it. That's not very difficult. You can simply use Vy as this formula root over of u sin square alpha minus 2gh and divide by u cos alpha. You can take it inside the square root and you end up getting root over of cos alpha minus 2gh upon u square cos square alpha. In that way, you could write it down if you wish. Okay. Let's take up an example question before we leave it for today. That will be the last thing we do. Then from next class, we can consider some more things about this. Suppose that there's a particle which is projected at an angle of elevation that is sine inverse of 4 by 5.
Sir, repeat the question, please.
Okay, write down the question. I'm just reading it out. You write it down. Okay. Okay. The question says a particle is projected. A particle is projected at an angle of elevation sine inverse 4 by 5. A particle is
53 degree.
What?
53 degree.
That is approximate. It is not exact.
Sine inverse.
4 by 5. It's given sine inverse 4 by 5. That's okay. So elevation sine inverse 4 by 5 and its range on the horizontal plane is 3 kilometers. Okay, a particle is projected at an angle of elevation sine inverse 4 by 5 and its range on the horizontal plane is 3 kilometers. So find the velocity of projection. Find the velocity of projection. I mean the speed actually. Time of flight and the velocity at the highest point. Determine the speed of projection, the time of flight, and the velocity at the highest point of the path. Okay. You can take it as yes, 10 meter per second square. You can just consider it. The range is 3 kilometer. 3 kilometer. 25 square root 5 meter per second. That is the launch speed. Given roughly 170. Last 3-4 minutes in short. Anika, I just gave a question. It says that a particle is launched at an angle of sine inverse 4 by 5 so that the horizontal range is 3 kilometers. You have to find out the speed of projection and the speed of projection is to be figured out and time of flight is required and the speed at the highest point is also required. 25 root 5. No, that is not correct actually. Root 75 for 5 root 5 by 2 is how, what is Shant? It is time of flight. Well, I mean the number is sine inverse 4. I know it. Okay, just let me see. One light is on. U is 5 root 10 by 2. Shubham donation is too small by the way. 100 into root 3. Avibrata, what is? Five root 5 by 2. Atul. Yeah, it's 125 square root. That is fine by the meter per second. Yeah, so 125 root 2 meter per second is what we have. Yeah, it's actually 125 root 2. Check for the units by the way. The 3 kilometer must be converted to 3000 meters.
Sir, 20 root 2 is coming as time.
How much?
20 root 2.
20 root 2. Okay, twice u sin alpha by g is what you have. U is 125 root 2 to 50 root 2, 4 by 5. 50 root 2 into 4 by 10. I get in this case 20 root 2 second. Yeah, that's fine. 20 root 2 second is a time.
Sir, the speed at highest point is coming 75 root.
Okay, that's fine. Just u cos alpha is what we want. We get 125 root 2 into 3 by 5. So that makes it 75 root 2. Yes. Okay. Yes, 75 root 2 meter per second. That is what you have to have. Yes, Pranjana is fine. 125 root 2 is a velocity projection. Yeah, that is correct, Anushka. Projection speed is 125 root 2 meter per second. Time of flight is 20 root 2 seconds. And speed at the highest point is 75 root 2 meter per second. Yes, that's fine. You people do not write the units. Always write it down by the way. I hope you are writing in the copies, not over here, but maybe in copy you should write down. 20 root 2 meters, this time is meter, Ranavo. 20 root 2 is, second, not meter, but I'm saying that. 20 root 2 second is a time. The speed of launching is 175 root 2 meter per second. And the highest point speed is 75 root 2 meter per second. Okay, no problem. Okay. Yes, Anushka is correct. Okay, fine. In that case, okay, Atul, rectified mistakes. You have to take units into account as well. Okay. So if we take it, that will be all today, by the way. We have already done the horizontal projectile. We shall do some more question next time, and we'll take up the projectile on an inclined surface as well. Meanwhile, the questions which are impending or pending rather, those questions I shall just try. You might try it as well, but again, I should try it later. Okay. Yes, that's fine, Anushka. 75 root 2 meter per second is the speed of the highest point. Okay. Yes, Anik, I will see. Anik question. Yes, I remember. You see, g sine theta is the acceleration in the upward direction. So we can just take the reference as the box itself. I think the diagram there is a mistake possibly. If they have just given the acceleration g sine theta downwards, it would have become very, very easy actually. Because then the path will be simply perpendicular to the inclined surface. But in this case, they have given it upwards. That gives a bit of a problem. Okay. Okay, no problem. The answer will definitely come, but how much you get by the Pradeep?
Sir, cot theta is equal to 8.
8 coming. Okay, fine. Okay, fine. Either you can post the solution, otherwise I'll just have to do it and send later on.
Okay, sir.
Okay. Okay. Okay, then good night for today, by the way.